I am from the University of Minnesota. University of Minnesota. Minnesota is here in the United States, and the University of Minnesota is in the city of Minneapolis and St. Paul. And I've been teaching there for the last 20 years, and the last 10 of them, or 11, on this topic of carbon, climate change, renewable energy. You students are graduating soon, and the previous generations, have left you lots of things to consider and think about. Problems, I might say. We have pandemics, we have racism, we have population explosion, we have resource depletion, we have environmental degradation, and we have climate change. Lots of stuff to consider. I'm focused right now today on climate change, and I hope that I can bring you some of the elements of the climate change issue, and also be a little bit hopeful on where we're going with this. So my first topic then is climate, and this image is one that I like to begin with because this is a picture of Earth from outer space. Often we think that the atmosphere that we have is infinite, that it goes on, and when we dump pollutants into the atmosphere, it goes out into space and it's gone. But our atmosphere is very thin. About 90% of what we talk about as atmosphere, the mass of the gases in the atmosphere, are within 30 kilometers of the Earth's surface. So if you walked straight towards the sky for 6 hours, you would be out of the atmosphere, most of the atmosphere. If you took your car and drove 20 minutes, you'd be out of the atmosphere. So I think a lot of times we don't think about how thin that atmosphere is, and that's what protects us from the elements of outer space. That atmosphere is filled with nitrogen, oxygen, argon. About 99% of it is this. Less than 0.1% is other gases, carbon dioxide, methane, and a bunch of other lesser gases. These are important gases, though, these small fractions of gases, and it's because of our global energy balance. So when we think about global energy balance, if we have energy coming in from the sun, energy from the sun is here, coming to Earth, it hits the Earth, and the energy hitting Earth has to escape back into outer space. If it doesn't balance the energy input and the energy output, the Earth heats up, or the Earth cools down, and it will make it a place that we can't live anymore. So our life on this planet, all our vegetation, is a function of that energy balance. Energy in equals energy out. So the energy in is this sun, and the energy from the sun, the distance the sun is from the Earth, which those two are fairly constant. They have some cyclic patterns, but are fairly constant. And this has to meet this energy output being reflection of the sun's energy back into space from the atmosphere and from the land surface. And also, there's a trapping of the energy by greenhouse gases, such as carbon dioxide and methane. We need those trapping gases, otherwise we would be like the moon, where it heats up a lot during the day when the sun is shining, and then it would cool down so much at night there'd be no chance for life to be on this planet. So we need some of that energy, or those greenhouse gases, to hold in some of that heat temporarily, but we also need it to release those gases. So energy in equals energy out. What has happened recently that we've been monitoring these greenhouse gases, and one of them we'll focus on is carbon dioxide, that we have in the past had about 200 to 300 parts per million, or about 0.03% carbon dioxide in the atmosphere. Recently, we have been measuring carbon dioxide in the atmosphere, and it is now up to 420 ppm, or about 0.042%. So only within the last 100 or so years have we seen this sharp increase in carbon dioxide concentrations, which then is one of those greenhouse gases that traps this energy. We can look at that average temperature of the globe and say that over time we have seen this temperature being fairly constant over time. And even with slight increases in highs and low temperature, we will get warming periods or even an ice age based on slight differences in this global temperature. Well, now our global temperature is up about 1 degree higher than normal. And that doesn't seem like a lot, but that is a significant change in our global temperature because of that carbon. That climate change, that warming of the climate, results in climate change, which means extreme weather events. All this additional energy in the atmosphere creates extreme weather events, rainfall events, harsh rainfall, winds, hurricanes, droughts, changing climate patterns, frost and heating, and sea level rise. So lots of things that I'm sure you've heard about that result from this climate change. The other next section of this talk is about carbon. Slide the blue line right now.
That's right.
Okay, that's my coolest picture. So what I talked about was this atmosphere, just a thin blue line over the top of the earth where all our gases are. And these are my cool things that I talked about, but you didn't see. The balance of the energy in from the sun versus the energy out from the sun. The carbon dioxide concentration shooting up significantly. We were back here in the 250 to 300 range, and now we're up at this 420 range. And this last slide that I had was on the temperature has changed over time, and just slight changes in atmosphere or global temperatures result in big changes in our climate. So a little ice age was only because the temperature was just a little bit below normal global average temperatures, and now we're way up here, almost a degree above normal temperatures, which causes climate change. And you all know about climate change and the hazards it's causing us. So now I think we're caught up with carbon, that we can look at this increase in carbon dioxide concentrations and say what happened that caused this increase over the last about 100 years. This scale is 800,000 years ago. When you look at this timeline, this is 800,000 years ago. We've seen this carbon dioxide in the atmosphere being fairly stable, and now we're way above that. And it is because of our carbon cycles. So we have a fast carbon cycle. This fast carbon cycle is plants, either land-based plants or ocean-based plants, algae and seaweed, taking carbon dioxide from the atmosphere, using that carbon dioxide as a building block for plant material. That plant material is then eaten by animals or degrades into the soil, and then it is released back into the environment as carbon dioxide. And so that is the fast carbon cycle, and that carbon isn't much of our global total carbon, but it's moving rapidly between the atmosphere, the plants, and the ocean. We also have a slow carbon cycle, and that slow carbon cycle is this rocks, ocean sediment, fossil fuels that have been buried, that are beneath the Earth's surface, that slowly move carbon from those sources into the fast cycle. And it slowly moves back from the fast cycle into the slow cycle. So what's happened recently, though, is that we've been taking carbon that was in the slow cycle and moving it rapidly into this fast carbon cycle through our burning of fossil fuels, putting more CO2 into the atmosphere. That CO2, like I said before, it doesn't leave our atmosphere. It doesn't go off into outer space. It is stuck here in our atmosphere, and it has to get recycled in this fast carbon cycle. So it either moves to the land, or it moves into the atmosphere, or it moves into the ocean. And so because it's moving into the atmosphere, that's why we're seeing this large carbon dioxide concentration increase in the atmosphere. We also see it on land base. There's vegetation and in soils that it's trying to absorb this extra carbon, and we're seeing it in oceans. Oceans, it's causing a shift in pH because of that carbon dioxide. We can verify this slow and fast carbon by looking at the concentration of atmospheric carbon dioxide. That's what this graph is. Since 1960, we've been doing some monitoring in Hawaii of carbon dioxide concentrations in the atmosphere. And this jagged sawtooth is the annual. So the Earth is like it's breathing between winter and summer, between the seasons. It's taking in carbon dioxide, releasing carbon dioxide. So we're seeing this fast carbon cycle in this jagged edge. And we're seeing the slow carbon cycle, that carbon that should be in the slow carbon cycle being transferred to the fast carbon cycle. And we're seeing it in this trend. It continues to increase. So atmospheric carbon is increasing because of that movement of carbon from fossil fuels into the atmosphere. So what is the point of all this? Well, the point is that our energy consumption on the planet is primarily fossil fuels, about 85%. In the past, it was 100% fossil fuels, but we weren't using that much energy. Over the last 100 or so years, we have dramatically increased our use of energy, all for good purposes. We're using our energy for transportation, for heating our homes, for all the computers, lighting, all that stuff that we do to have a healthy economy, to have a nice lifestyle. It's because of our fossil fuel use. Fossil fuels are cheap, they're easy to transport, really high energy density. So that means that in a kilogram of coal or a kilogram of petroleum, there's lots of energy. That means we can move that energy around and still benefit from that. So we can haul high density energy in our vehicles, so gasoline. But we also know that we can get energy from the sun. Almost all of our energy, even fossil fuels, was at one time energy from the sun. Fossil fuels were, of course, buried biomass, plant material, and it concentrated that energy into our fossil fuels now. But there's enough energy in 1 hour from the sun to power the world for a year. The challenge to us is that we need to concentrate and capture that energy from the sun, and that's not easy. The sun's energy source is really diverse and spread out, and we need to figure out how to concentrate it into a useful form. So that's our challenge. Plants were the first renewable energy system. Plants, through photosynthesis, they capture energy from the sun. Remember, they're capturing energy and carbon dioxide, and they are moving that into, converting it into chemical energy, starch, sugar, oils, cellulose, basically all the materials of a plant. That is a capture of solar energy. And we actually have been using that solar energy for a long time, renewable energy in the form of biomass, where we're cooking with biomass, wood, for centuries and centuries. We've been using that form of renewable energy. When this wood is then burned, the carbon dioxide is released into the atmosphere. It goes back into that fast carbon cycle. We have adapted that for our use in renewable energy to replace transportation fuels, to replace gasoline and biodiesel by taking the sugar and starch to produce ethanol. Ethanol is a replacement for petroleum. And we have taken the plant oils to produce biodiesel. Once again, this is a replacement for our transportation fuels. Now, it's not a perfect energy source because plants generally have really low energy capture. The energy capture from the sun and conversion into chemical energy is probably about at the most, it's 2% efficient for capturing that energy. That means that we have to use lots of land to capture just a little bit of energy from the sun. So our land use is an issue. We're converting what could be cropland, feeding the world, into energy crops. And I think that's what some people are upset about, reasonably so, that we are not doing a good job with our energy capture with plant materials. We can also, solar energy or energy from the sun creates our climate conditions, which creates our wind, different pressures across the planet. And so we generate wind. We can capture some of this wind energy in these large wind turbines. As the wind turbines spin, they turn a generator that produces electricity. That works well, and that electricity then can replace coal and natural gas that we currently use to generate electricity. One of the problems with wind is that it has a variable output, meaning that the wind is not blowing all the time. When we generate electricity, we have to use it the same time it's being generated. So we have to match electricity supply and demand all the time. So with wind, it's difficult because the wind is not blowing, and yet we're wanting to use electricity. So we need lots of wind turbines. We need to have them spread out in large areas because it's low density energy source again. So we're using lots of land. And often that land that we're using is in rural areas where we're conflicting with other land uses, be it farming, be it indigenous populations that are being subjected to these wind turbines. There's noise, there's other issues with wind turbines. So lots of people don't like wind as an energy source. We can also use solar energy directly from the sun. These solar panels or photovoltaic panels can convert through chemistry solar energy directly into electricity. They're about 15 to 20% efficient, but even so, we need large land area to produce that electricity. It has a variable output, meaning that sometimes you want to use electricity at night and the sun isn't shining at night. So we have a mismatch between when the sun is shining and when the electricity is being generated and when we need to use it. So once again, matching of supply and demand is an issue. Land use, we're putting in areas where maybe there should be farmland, maybe we should be growing crops, maybe it's in deserts where we want to keep that natural area. We also have a problem with wind turbines and solar panels in that we're using material resources that need to be mined. So our mining practices for copper or for silicon or all the elements that go into these renewable energy technologies have to be mined, and we don't always do that very well. So lots of complaining or issues with solar energy also. Moving on to another energy source from the solar energy. Our sun, our energy on our planet creates rainfall, which creates rivers, which then can be dammed up where we generate enough elevation that when the water falls, we can capture that energy. So the dams create the potential energy, and they then, as the energy comes through those dams and through a turbine, we can generate electricity. Hydroelectric is really efficient. It's a really good source of electricity because we can turn that on and off whenever we want it. That energy is there all the time. So we can match the supply and demand really easily with our hydroelectric sources. However, when we dam up the rivers, it's not a perfect system because we are displacing people that lived along those rivers. We are changing the ecosystem. It's not a perfect system either. There's also discussion about when we flood all those areas, there is methane generation from that flooded area. And so that is creating some greenhouse gases that we didn't anticipate. Despite all that, we are increasing our renewable energy production significantly. We were at about 3% back in the 1960s, and we're at 11% of our energy is generated by renewable energy. So it's been growing rapidly. It continues to grow rapidly. It's now cheaper than fossil fuels. So solar panels, wind turbines are now cheaper. The technology has come down in price, just like the price of a television or a computer has come down. the more we use it, the more that technology develops. So we're getting more efficient at renewable energy technologies. We're also integrating that energy into our energy system better. So our electric grid, our fossil fuel pipeline, or our petroleum pipelines, natural gas pipelines, we're able to integrate that better with renewable energy. We are developing battery technologies that we can use. When we talked about the solar energy and wind energy not being available all the time, we are now developing battery technologies that we can store that energy when the sun isn't shining or the wind isn't blowing. We're also looking at carbon pricing. So yes, renewable energy is cost competitive now, but if we looked at the damage caused by renewable energy, that we should include that in the cost of fossil fuels. And I think more policies are going in that direction. So we are now paying for the environmental degradation caused by climate change and other environmental issues with fossil fuels. So it's moving quickly in the direction of renewable energy generation. I think that it is a daunting task to say that we are, like have climate change and we are out of control. And it is a challenge. And we cannot all be Greta and being that activist voice, but I think we can all make a difference. I relate it to voting here in the United States or anywhere else. Your vote counts. It's just one vote out of many millions maybe, but your vote counts. So I think there are some things that we can do as individuals, and that is to take care of ourselves. So that means we're not wasting energy. That means like we're turning off televisions, we're turning off lights, we're doing what we can on our own to do our best. Food waste is wasting of energy. So we use lots of energy for our agricultural systems to grow our food. We're using energy, and by wasting our food, we're wasting energy. So another simple thing that you can do that can have an impact. Generally consuming less. We buy less things. Every time we buy an iPhone or a new toy, that toy has energy embedded in it. It takes energy to make that toy. It takes energy to use that toy. So we need to stop consuming. Also, I think improving our knowledge of the issues, studying carbon cycles, studying climate change, studying our energy system. So we are knowledgeable about what is going on in the world is really important.